Good morning students, this is Latif sir. In this video, I am continuing the second chapter of class 12th chemistry. The topic is solutions. In the first video, I have discussed about different types of concentration term, that is molality, mole fraction, normality. And today, in this video, I will discuss about solubilities, Henders law, Raoult's law, ideal solution, non-ideal solution, and agiotopic mixture or constant boiling mixture. In this chapter, mainly you have to read about three types of solutions: gas in liquid solution, liquid in liquid solution, and solid in liquid solution. You know, a solution is formed by combination of two components. One is known as solvent, another is solute. And different solute are soluble in a particular solvent at a particular temperature in different amount. Okay, that is solubility of different solute are different in a particular solvent at a given temperature. So first you have to know what is solubility. Solubility is the maximum amount of a solute, that can be dissolved in a given amount of solvent, generally in 100 gram of solvent at a given temperature. Solubility is the maximum amount of a solute that can be dissolved in a given amount of solvent, generally in 100 gram at a given temperature. For example, if at 40 degrees Celsius in 100 gram water 35 gram NaCl is dissolved, then solubility of NaCl at 40 degrees Celsius is 35. Okay, now see factors on which the solubility of a solute depends. The factors are nature of solute, nature of solvent, temperature of the solution, and pressure. In case of gases, the factor pressure, this factor is applicable mainly in case of solution of gas in liquid. Okay, now see Henry's law. What is Henry's law? And this law is applicable for solution of gas in liquid. For solution of gas in liquid, you know, higher the pressure above the solvent, above the solution, higher is the solubility of the gas in the solution, in the liquid or in the solvent. Okay, that means the solubility of a gas in a particular solvent is directly proportional to the pressure above the gas. And here the amount of gas dissolved in a particular amount of solvent is expressed in terms of mole fraction of the gas. Mole fraction means x. X is the mole fraction of gas. If the pressure above the gas is P, then amount of gas dissolved, that is which is expressed in terms of mole fraction. Okay, if X is the amount of gas dissolved, X is the mole fraction of the gas, which is expressed in mole fraction, not in mass. According to Henry's law, you can write P proportional to X. Higher the pressure above the gas, higher is the solubility of the gas in solution. That is P proportional to mole fraction of dissolved gas. Okay, this is according to Henry's law. You can state Henry's law like this: the partial pressure of the gas in vapor phase is proportional to mole fraction of the gas in the solution. The partial pressure of the gas in vapor phase is proportional to mole fraction of the gas in the solution, and it is expressed as P proportional to X, or you can also write P is equal to some constant which is kh into X, where kh is known as Henry's constant. Amount of gas dissolved, that is mole fraction of gas, is directly proportional to pressure above the gas. So P proportional to X. Now you can omit the proportionality sign, and you have to use a constant which is kh. Kh is is a proportionality constant which is known as Henry's constant, and this Henry's constant is different for different gases. Okay, so pressure, if pressure above the gas is high, then solubility of the gas in the solvent will be high. Okay, and now see characteristic of the Henry's constant kh. Kh is known as Henry's constant. Greater the value of kh, that is Henry's constant, higher is the solubility of the gas. Greater the value of Henry's constant, that is kh, higher is the solubility of the gas. And the value of kh decreases, the value of Henry's constant kh decreases with increase in temperature. If temperature is high, then value of kh for a particular gas, if temperature become high, value of kh will be decreases. Okay, now see applications of Henry's law constant. Applications, sorry, applications of Henry's law. This is application of Henry's law. There are many important applications of Henry's law. For example, in manufacture of soft drinks, and soda water, carbon dioxide is passed at very high pressure to increase the solubility of carbon dioxide in water. Or in soda water, in soft drinks, carbon dioxide is mm, carbon dioxide is mixed with water by applying very high pressure. This is a good application of Henry's law. Similarly, one more application is given to minimize the painful effect accompanying the decompression of deep sea diver. Oxygen diluted with less soluble helium gas is used as breathing gas. Okay, so these are some applications of Henry's law. So you have to remember the statement of Henry's law with mathematical equation and one or two applications also, and characteristic of Henry's law constant kh. Now see liquid in liquid solution and vapor pressure of a solution. Liquid in liquid solution, and Raoult's law related to liquid in liquid solution, like Henry's law is related to gas in liquid solution. Similarly, Raoult's law is related to liquid in liquid solution, in which both solvent and solute both are liquid. And the heading is vapor pressure of a solution. Vapor pressure of a solution. You know, all liquids are more or less volatile. All liquids. Some liquids are more volatile and some liquids are less volatile. Like petrol, diesel, these are more volatile liquid, and water is less volatile liquid. Okay, so all liquids are more or less volatile. In a closed container containing a liquid-liquid solution, the space above the solution contains the vapor of all the components. Suppose in a closed container you have taken a mixture of two liquids, in which one is more volatile, another is less volatile, but both are liquid and both are volatile liquid. And now if you suppose you have taken two volatile liquid here, and after some time you will see that in the vapor state, after some time you will see that in the vapor phase, in the vapor state, in this space you will get the vapor of both the liquids, that is liquid, suppose here liquid A and liquid B are B are mixed to form a liquid solution. And after some time you will see that in the space just above the solution, and solution is kept in a closed container, and after some time you will get a vapor pressure of both liquid, in this space just above the solution. Okay, so now say Raoult's law, that is how the vapor pressure, of the volatile liquids, how the vapor pressure of the volatile liquids depends on the mole fraction of the liquids in the solution. I have told that Raoult's law is applicable for liquid in liquid solution. Now you have to suppose you have a solution, you made a solution by mixing two liquids, liquid A and liquid B, in a closed container. And after some time you will see that in the space just above this solution, both vapor of all the components, vapor of components A and components B, that is vapor of liquids A and liquid B, will get in the space just above the solution. Okay, and you can calculate the vapor pressure of liquid A and liquid B by using Raoult's law. And Raoult's law states that for a solution of two volatile liquids, in which one is more volatile and another is less volatile, suppose liquid B is less volatile, more volatile than liquid A. Okay, so Raoult's law states that for a solution of two volatile liquid, the vapor pressure of each liquid in the solution is less than respective vapor pressure of pure liquids. Vapor pressure of each liquid in the solution will be less than vapor pressure of pure liquid. This point you have to remember, that always vapor pressure of any liquid in solution is always less than vapor pressure of pure liquid. Okay, so according to Raoult's law, for a solution of two volatile liquid, the vapor pressure of each liquid in the solution is less than the respective vapor pressure of pure liquids, and the equilibrium partial vapor pressure of the liquid, equilibrium partial vapor pressure of the liquid is directly proportional to its mole fraction. That is, in equilibrium condition, the vapor pressure of both the liquid is directly proportional to its mole fraction in the solution. Suppose vapor pressure of liquid A, in the equilibrium vapor pressure of the liquid A is Pa and its mole fraction is Xa, then according to Raoult's law, Pa is proportional to Xa. Suppose in the solution mole fraction of liquid A is Xa and equilibrium vapor pressure of A is Pa, then according to Raoult's law, Pa is proportional to Xa. And remember that always vapor pressure of liquid in solution is always less than that of pure vapor pressure of pure liquid. Suppose vapor pressure of pure liquid is Pa naught. Suppose vapor pressure of liquid A is Pa naught and equilibrium vapor pressure in the solution of A is Pa, then Pa is less than Pa naught. Similarly, if equilibrium vapor pressure of B is Pb in solution and vapor pressure of pure liquid B is Pb naught, then Pb is less than Pb naught. Okay, so vapor pressure of a liquid in solution is always less than vapor pressure of pure liquid. Okay, so according to Raoult's law, you can write, for a solution containing two liquids, liquid A and B, the partial vapor pressure of liquid A is Pa is proportional to Xa according to Raoult's law, where Pa is the partial vapor pressure of liquid A and Xa is the mole fraction of A in in solution. So according to Raoult's law, Pa proportional to Xa. Now Pa is equal to K into Xa, where K is a proportionality constant and Xa is the mole fraction. Okay, and mole fraction, you can calculate mole fraction by using this formula. A mole fraction is equal to mole number of that component divided by total mole number present in the solution, that is Na divided by Na plus Nb. Okay, Mole fraction of any component is equal to mole number of that component divided by mole total number of moles present in the solution. Now if value of Xa is 1, if value of Xa is 1, that means mole fraction is 1. Mole fraction of A is 1. If mole fraction of A is 1, it indicates pure liquid A. Pure liquid A. Okay, so when mole fraction of liquid A is 1, it means that it indicates pure liquid. Pure liquid means its vapor pressure will be Pa naught. Pa naught. So when Xa is 1, then you can write K is equal to Pa naught. When Xa is equal to naught, Xa is equal to 1, then you can write K is equal to Pa naught. Xa is equal to 1 means it indicates pure liquid A, not in solution. Okay, and the vapor pressure of pure liquid is represented by Pa naught. Vapor pressure of pure liquid A is represented by Pa naught. So you can also write the Raoult's law like Pa is equal to Pa naught into Xa. Pa is equal to Pa naught into Xa, where Pa is the partial vapor pressure of the liquid A in solution and Pa naught is the vapor pressure of pure liquid and Xa is the mole fraction of liquid A in the solution. Similarly for component V, according to Raoult's law, for liquid V you can also write Pb proportional to Xb, where Pb is the partial vapor pressure of liquid B and Xb is the mole fraction of the liquid B in solution. So you can also write Pb is equal to Pb naught into Xb. When Xb is equal to 1, it indicates that pure liquid B and vapor pressure of pure liquid is taken as Pb naught. So you can also write Pb is equal to Pb naught into Xb. That is, vapor pressure of liquid B is equal to vapor pressure, partial vapor pressure of liquid B is equal to vapor pressure of liquid vapor pressure of liquid B in pure state into mole fraction of liquid B. That is, Pb is equal to Pb naught into Xb. Now total vapor pressure of the solution can be obtained by adding Pa plus Pb, vapor pressure of A and vapor pressure of B. So P, total vapor pressure of the solution, is equal to Pa plus Pb, where Pa is equal to Xa, Xa naught, Pa naught Xa, and Pb is Pb naught Xb. Okay, so after generalization you can get this relation: P, total vapor pressure of the solution, is equal to Pa naught, that is Pa naught, that is vapor pressure of A in the pure state, plus Pb naught minus Pa naught into Xb. Okay, so using the Raoult's law for different component, different liquid component in a solution, you can calculate the total vapor pressure of the solution. Now say ideal solution. What are ideal solution? Ideal solutions are those solutions which obey Raoult's law. Okay, so those solution in which solute, solvent, and solute-solvent, all this type of interaction are similar. Okay, so in those solution in which ideal solution are those solutions in which solute, solvent, and solute-solvent, all these three types of interactions are similar. And now say conditions For formation of ideal solution or ideal solution satisfy the following conditions. First one is ideal solution must obey Raoult's law over the entire range of concentration. Ideal solution must obey the Raoult's law. That is, for each component of ideal solution, you can apply the Raoult's law over the entire range of concentration. Okay, thus for the binary solution of two liquid A and liquid B, while liquid A is less volatile than liquid B, you can write, applying Raoult's law, you can write PA is equal to PA naught XA and PB is equal to PB naught XB. And as the liquid B is more volatile than liquid A, PB naught is greater than PA naught. Okay, and this is the vapor pressure versus mole fraction diagram for ideal solution. Okay, and here some example of ideal solution are given. Example of ideal solution: benzene plus toluene, mixture of benzene and toluene, mixture of n-hexane and n-heptane, mixture of ethyl iodide, ethyl bromide, mixture of chlorobenzene and bromobenzene. All these are some examples of ideal solutions. And for ideal solution, the vapor pressure versus mole fraction diagram is this one is the vapor pressure versus mole fraction diagram for ideal solution. Okay, and I have told that vapor pressure of pure B, liquid B, is more than vapor pressure of liquid A. That's why PB naught is value of PB naught is higher than value of PA naught. Okay, and in this axis, mole fraction of A, that is XA is 1 and XB is equal to 0. That means along this axis it indicates pure liquid A, and along this axis value of XA is 0, value of XB is 1. That is, this line indicate this is for pure liquid B. Okay, and in between these two axes, in between these two axes, two line, these values are indicating solution state. Okay, that is, here this is pure liquid A, and this in this axis it is pure liquid B, and within these two axes this is for solution, that is mixture of liquid A and liquid B. Okay, and according to Raoult's law, as the mole fraction of any component increases in the solution, its vapor pressure will be increases. Okay, from left to right, value of XA decreases. From left to right, value of XA, that is mole fraction of liquid A, decreases. So from left to right, partial vapor pressure of liquid A decreases from left to right. Similarly, from left to right, mole fraction of B increases from 0 to 1. So from left to right, partial vapor pressure of liquid B increases from left to right. Okay, and total vapor pressure is obtained by adding vapor pressure of A and vapor pressure of B, and this line is for vapor pressure of solution, total vapor pressure of the solution. Okay. Now see next condition for of ideal solution: delta H mixing is equal to 0. That means no energy evolved or absorbed during the formation of ideal solution, and delta V mixing is also 0 for ideal solution. That is no expansion or no expansion or contraction on mixing. Volume remains same before and after the making the solution. Okay, so these are some conditions for ideal solution. Ideal solution obeys these conditions. Ideal solution always obeys Raoult's law. That is, for each component of ideal solution you can apply the Raoult's law. Okay, and you have to remember the some examples of ideal solution also. Now see non-ideal solution. What are non-ideal solution? Non-ideal solution are those solution in which uh, shows deviation from Raoult's law. Ideal solutions, they obey Raoult's law, but non-ideal solution, they do not obey Raoult's law. Okay, so those solution which show deviation from Raoult's law is called non-ideal solution. In non-ideal solution, different types of interaction, that is solvent solute, these different type of interactions are not equal. But in ideal solution, this different type of interaction between solvent and solute are equal. But in non-ideal solution, different types of interaction are not equal. Okay, so you cannot write Pa is equal to Pa not Xa for a non-ideal solution. So for non-ideal solution, suppose A and B, two liquids A and B mixed together to form a non-ideal solution, and I have assumed that this is a non-ideal solution, so you can't write that Pa is equal to Pa not Xa. For non-ideal solution, you have to write Pa not is equal to Pa not Xa. Similarly, Pb not is equal to Pb not Xb. And for non-ideal solution, delta H mixing not is equal to 0. Okay, so non-ideal solution so two type of deviation. Non-ideal solutions shows two types of deviations from ideal behavior, ideal solution. One is positive deviation, another is negative deviation. So first see positive deviation. Non-ideal solution showing positive deviation. In case of positive deviation, the vapor pressure of the solution will be higher than the vapor pressure uh, of ideal solution. Okay, this is the vapor pressure of non-ideal solution, and this is higher than the ideal value. This is ideal value, and this is for non-ideal solution. Okay, and in case of non-ideal solution, vapor pressure of liquid A, liquid B, vapor pressure, partial vapor pressure of all these component are higher than that of ideal values, and that is why it is called that is why this is positive deviation. This such type of positive deviation are showing by such non-ideal solution. So non-ideal solutions showing positive deviations, in such case the AB, that is solvent solute interaction, are weaker than solvent solute interaction. In case of non-ideal solution showing positive deviation, the solvent and in case of non-ideal solution showing positive deviation, the solvent solute interaction is weaker than solvent or solute solute interaction, and the observed vapor pressure of each component and the total vapor pressure are greater than that predicted by Raoult's law. Okay, so for non-ideal solution showing positive deviation, you can write Pa is greater than Pa not Xa, and Pb is greater than Pb not Xb, and total vapor pressure of the solution, that is P is greater than Pa plus Pb, that is P is equal to Pa not Xa plus Pb not Xb. And this diagram is for non-ideal solution showing positive deviation. Okay, and in case of positive deviation, delta V mixing is greater than 0, delta H mixing is greater than 0. And now example of such solution which showing positive deviation: uh, water and ethanol, carbon disulfide and acetone, mixture of carbon tetrachloride and benzene, carbon tetrachloride and toluene. Mixture of this two liquids, carbon sulfide and acetone, or ethanol and water, this solution act as non-ideal solution showing positive deviation. And now see non-ideal solution showing negative deviation. non-ideal solution showing negative deviation. In such case, the vapor pressure of the solution will be lower than the ideal value, and vapor pressure of each component also, vapor pressure of liquid A, vapor pressure of liquid B will be less than that of ideal value. So in non-ideal solution, in case of non-ideal solution showing negative deviation, in such a case the solute solvent interaction are stronger than solvent solvent or solute solute interaction. In case of non-ideal solution showing negative deviation, the solvent solute interaction are stronger than solvent solvent or solute solute interaction. And in such case, the observed vapor pressure of each component and the total vapor pressure of the solution are lesser than that predicted by Raoult's law. Okay, so in case of non-ideal solution, the vapor pressure, observed vapor pressure of each component and the total vapor pressure of the solution are lesser than that predicted by Raoult's law. That is, in case of non-ideal solution showing negative deviation, you can write PA less than PA not XA and PB less than PB not XB. Similarly, total vapor pressure of the solution, P is less than PA plus PB, or P is less than PA not XA plus PB not XB. And for such solutions non-ideal solutions showing negative deviation, delta H mixing is less than 0, delta V mixing is less than 0. Okay, and this diagram showing the variation of vapor pressure versus vapor pressure with mole fraction for non-ideal solution. Okay, example of non-ideal solutions showing negative deviations are chloroform and acetone CaCl3 plus acetone CH3COCH3, chloroform and benzene, water and HCl, water and nitric acid. These are some example of solution which shows negative deviation from ideal behavior or from Raoult's law. And now see agiotopic mixture. What are agiotopic mixture? Agiotopic mixture, it is also called constant boiling mixture. Okay, it is a solution of a mixture of two liquids which boil at a particular temperature like a pure liquid and distill over in the same composition is known as constant boiling mixture or agiotopic mixture. These are generally Agiotopic mixture are generally non-ideal solution. These are mixture of two liquids. Okay, and this mixture, agiotopic mixture, boil at same temperature. Both the component of such agiotopic mixture start boiling at same temperature like pure liquid. Okay, so a mixture of two liquids which boils at a particular temperature like a pure liquid and distill over in the same composition is known as constant boiling mixture, and these are formed by non-ideal solution. There are two type of agiotopic mixture or constant boiling mixture. One is minimum boiling agiotopes and maximum boiling agiotopes. Minimum boiling agiotopes are formed by those liquid pair which show positive deviation from ideal behavior. Minimum boiling agiotopes are formed by those liquid pairs which show positive deviation from ideal behavior, and such agiotopes have boiling point lower than either of the components. For example, mixture of ethanol and water, 95.57% ethanol and 4.43% water. This mixture act as minimum boiling agiotopic mixture. And now see maximum boiling agiotopes. These are formed by those liquids pair which show negative deviation from ideal behavior. Maximum boiling Agiotopes are formed by those liquid pairs which show negative deviation from ideal behavior, and such agiotopes have boiling point higher than either of the components. Example of such maximum boiling agiotopes: mixture of water and HCl, 20.22% water and 79.78% HCl. This mixture is act as maximum boiling agiotopic mixture. Okay, and next day I will discuss about colligative property. Okay, so today I have discussed about solubility, Henry's law is important and its application also you have to remember. And for solution of two liquids, you have to remember the Raoult's law, statement of Raoult's law, ideal solution, non-ideal solution, and conditions for ideal solution, conditions for non-ideal solutions. Okay, and variation of vapor pressure with mole fraction for ideal solution, for non-ideal solution, and what are agiotopic mixture or constant boiling mixture with example you have to remember. Okay, thank you students.